As the 19th century drew to a close, the periodic table's ability to corral the elements contributed to a growing sense that the work of science was just about complete. Most of nature's building blocks had been found, measured, and cataloged. Chemists agreed these elements had been and always would be the same, forever fixed, unchanging. All that remained was to fill in the few remaining blanks. Or so it seemed. In fact, this smug sense of satisfaction was about to be shattered by something and someone completely unexpected. She was the unlikeliest of revolutionaries. A graduate student, a woman from Poland, who had left her homeland to pursue her passion for science in Paris. Yet in 4 short years, her discoveries would transform our understanding of matter and make her one of the most famous women in the world.
She worked on something that was relatively obscure and turned it into a blockbuster. New elements, new properties, and a whole new way to look at the world.
The world would know her as Marie Curie, but she was born Maria Skłodowska into a family of Polish patriots at a time when Warsaw was under Russian rule. Poland had been literally wiped off the map, its residents forbidden to speak their own language or teach their own history. But Maria's family secretly defied the Tsar, speaking Polish at home and reciting patriotic poetry to preserve their Polish heritage.
She used to go by an obelisk erected in honor of the Russian people and spit on the obelisk on the way to school. So you can see Maria learned early to be a fighter and resistor.
The daughter of 2 teachers, Maria excelled in science and math. But in Russian-ruled Poland, women were not allowed to attend university, let alone become scientists.
Very, very few places in Europe or elsewhere had opportunities for young women to study science. So one of the few places that she could was, in fact, in Paris.
But because her family was too poor to send her, Maria would first have to work for 6 long years as a governess to support her older sister's studies. Only at age 24 did she finally get her chance.
She waited her turn and she didn't give up. And when the turn came, she took it.
I was lost in the great city. But the feeling of living there alone and taking care of myself without any help didn't depress me at all. I had been waiting for this opportunity for a long time.
Paris in the 1890s was like no other place on Earth, a living showcase for the wonders of science and technology. The city boasted such modern marvels as electric streetcars and telephone exchanges. At the laboratories of Louis Pasteur, scientists were conquering diseases that had plagued humanity for centuries. The Lumiere brothers were thrilling crowds with their new invention, pictures that actually moved. And rising above it all was the brand new Eiffel Tower, which would remain the world's tallest structure for nearly half a century.
Here was Paris, the kind of intellectual, artistic, technological capital of the universe. This is where the modern age was born.
She felt this precious sense of liberty. She could say whatever she wanted, go wherever she wanted. She took it all in and loved it.
Everything I saw and learned was a new delight to me. I had only one regret. The days were too short and went by too quickly.
Adopting the French form of her name, Marie, she enrolled at Paris's preeminent university, the Sorbonne, where she could study under the leading lights of French science. One of them was Gabriel Lippmann, a future Nobel Prize winner.
Another was Henri Poincaré, who was one of the leading mathematicians of the 19th century. One of her math instructors was a mountain climber, another was an aviator. These were exciting people, scientists who had exciting lives.
It was like a new world opened to me, the world of science, which I was at last permitted to know in all liberty.
Marie graduated first in her class in physics, and with Professor Lippmann's help, received a grant to do research on magnetism. A friend suggested she seek out a French physicist who had studied the subject and might have some lab space for her. The meeting would change her life.
Pierre Curie seemed to me very young, though he was 35 at the time.
I think it was pretty much electric from the beginning.
With all my heart, I thank you for your photograph. I showed it to my brother Jacques. Was I wrong? He finds you very fine, but he also said she has a very decisive look, maybe even stubborn.
Pierre Curie was a first-rate researcher, but he had never bothered to complete his dissertation and was content teaching at an industrial college.
He was diffident, modest, and shy. He was very much an outsider. He'd been homeschooled by his politically radical father, along with his brother Jacques.
In a family photograph, you see him with his brother. His head is resting on his hand. It's a pose of dreaming, as if he is looking at some inner vision.
Pierre was a man of ideas, not action. But he was galvanized by this young woman and pursued her as he had nothing else in his life.
It would be a beautiful thing if we could spend our lives near each other, true to our dreams, in science, where every discovery, no matter how small, lives on.
Pierre's proposal posed a dilemma for Marie. She had planned to get a first-rate scientific education in Paris and then return to her beloved Poland to teach and care for her aging father.
Her mother died of TB early on, and he was counting on Marie coming back.
Now this ardent young man was offering her an exciting life as a working scientist.
It was a decision that would mean abandoning my family and my country.
Marie had all those feelings of responsibility for her father, for her family, and then for Poland on top of that.
In the end, their mutual devotion to each other and to science overcame Marie's resistance.
She wrote one of her friends, "Fate has brought us together, and we simply can't bear to be apart."
The newlyweds left on a cycling honeymoon after a simple ceremony in 1895. By 1897, even with a toddler to care for, Marie had set her sights on getting what no other woman had ever received in France, a doctorate in physics. At the time, the world was abuzz with excitement over a new discovery: mysterious rays that had the power to see through solid objects.
You could, by this process, look at the bones inside of your living hand. It's as if you had a magical set of glasses that lets you see inside of living creatures, and that sparks the public imagination.
Doctors instantly recognized X-rays as an invaluable diagnostic tool.
There was a great rush of excitement from working scientists as well. In that first year, there were about 1,000 scientific articles published at a time when the entire physics community in the world was only about 1,000 members.
But with so many others doing research on X-rays, Marie felt it would be hard to make an original contribution.
And so she picked something that she could work on where there was less competition. In fact, no competition.
Just a year earlier, a French physicist named Henri Becquerel had discovered a different kind of ray given off by the element uranium. These uranic rays were powerful enough to penetrate thick black paper and create an image on a photographic plate. But the images were not nearly as striking as those created by X-rays, and they seemed to have no practical value. So after writing a few papers about this scientific curiosity, Becquerel dropped the subject, thinking it had been squeezed dry.
Marie just thought that this was a tremendous thing to work on, particularly as a graduate student.
The subject was attractive to me because it was entirely new. Little had been written about it.
There was another reason Becquerel's uranic rays appealed to Marie. She had spotted a clue that might reveal more about them. As you can see, air is normally a poor conductor of electricity. The current can't jump this gap, so the bulb doesn't light. But Becquerel had noticed his uranic rays had the mysterious power to charge the air around them, allowing electricity to leak across. The amount of electricity was incredibly small, about 1/trillionth the amount needed to light this little bulb. No meter of the day could measure it. But Marie had a secret weapon Becquerel didn't.
Right in Marie's own household was perhaps the world expert in how to measure tiny little electrical effects. The two of them, Pierre and Marie Curie, designed this really quite ingenious instrument to measure these very subtle electrical effects from her samples.
They placed a layer of uranium on a metal plate, then charged the plate with a battery. As expected, electricity leaked across the gap to the plate above. To measure this tiny current, the Curies would use this second device to create a matching amount of electricity. Inside was a special crystal that could generate its own tiny charge thanks to a phenomenon called piezoelectricity. More than 20 years earlier, Pierre and his brother Jacques had discovered that certain crystals give out electricity in response to pressure.
The amount of electricity generated when you squeeze or stretch that crystal depends precisely on how hard you press on that crystal. And that means you have a way to make a very, very sensitive measurement of minute little electrical currents.
By placing a weight on the pan below, Marie stretched the piezoelectric crystal inside the device. Then, by slowly relieving the tension, unstretching the crystal, she could generate a charge exactly offsetting the one coming from her uranium sample. She could tell the two charges were equal when the spot of light from this third instrument was at 0 on the scale.
Though it didn't look very pretty, this sort of pulled-together little contraption was exquisitely accurate and could allow them to make measurements like no one else in the world.
But using these instruments required extraordinary concentration and dexterity. Ever so gradually, Marie relieved the tension on the crystal, while carefully watching the spot of light to keep the two charges in balance, and timing how long it took to lift the weight entirely off the pan. The faster she had to remove the weight, the stronger the activity of her test sample.
And that's why when you see pictures of Marie Curie in this experiment, she's sitting there with a stopwatch.
Oh, la petite étudiante. C'est très bien.
I never dreamt that I was about to embark on a new science that Pierre and I would follow for the rest of our days.
Day after day, working in a cramped, unheated storeroom, Marie painstakingly carried out her measurements. She compiled data on uranium, then went on to test the other known elements to see if any of them could also electrify the air.
She was not expecting to make any sort of earth-shattering discoveries.
She thought she would do some sort of diligent work on a whole lot of elements, and she would measure their power.
Exactly what you'd expect for a perfectly legitimate PhD dissertation.
And for a while, the results were predictably dull. No other elements showed this strange property.
Things were going along pretty routinely until one day in February of 1898, and that was the day that everything changed.
Pierre, viens voir.
In the course of a single week, Marie made two startling discoveries. She found that the element thorium could also make air a better conductor.
That was the first real solid indication that this was not unique to uranium. This might be a property of matter, not a curiosity of one particular element.
It was necessary to find a new term to define this new property of matter. I proposed the word radioactivity.
The next surprise came when Marie tested pitchblende, the raw ore from which uranium is taken. Something was very wrong.
C'est comme ça. T'es sûr des résultats?
Je ne suis pas sûre.
Pitchblende seemed to be 4 times as radioactive as uranium itself.
When I find a result like that, as a scientist, my first reaction is, I made a mistake, or the machine isn't working.
She did what every good scientist should do, which was doubt it, be extremely skeptical, and check every last step of that chain.
So my mother made her measurements over again. 10 times, 20 times, until she was forced to accept the results.
In time, the Curies realized this was no mistake. The readings from pitchblende were real.
A light bulb went off and they said, well, maybe there's something else in there.
Very soon, they began to suspect that there was another element in pitchblende, which was producing this enormous radioactivity.
There must be some new thing under the sun, some new element that had never been seen before.
And it must be intensely radioactive, since it was present in amounts so small that no one had ever detected it.
Since neither Marie nor Pierre was a member of the Academy of Sciences, they asked Marie's mentor, Gabriel Lippmann, to deliver the paper announcing this discovery.
This was one of the most important papers in the history of chemistry, and yet it was almost universally ignored.
Who was this Marie Curie? She was a graduate student. She spoke French with a Polish accent. She was married to a teacher in an industrial school, and she was a woman.
These are strikes that are definitely against you. And so her ideas just weren't embraced because she was so different.
But Marie knew she was onto something important.
She had lit upon, almost by accident, an extremely exciting discovery. And as soon as he figured that out, Pierre abandoned his work on crystals and joined her.
To track down their mystery element, Marie and Pierre subjected pitchblende to a battery of chemical procedures.
You break up your rock, you try to dissolve it, you treat it with all kinds of other chemicals.
The goal is to separate the ore into portions with different chemical properties, all the while tracking the radioactive signal.
She then throws away everything that isn't radioactive. It's getting more and more concentrated as she goes through these steps.
The Curies soon discovered that two distinct parts of the pitchblende, with different chemical properties, were both radioactive. That meant not one but two new elements might be hidden in the ore.
By July 1898, they were able to announce the discovery of one of those substances with certainty.
Marie, you will have to name it.
The former Mademoiselle Sklodowska thought of her occupied native country, whose very name had been erased from the map of the world.
Could we call it polonium?
Poland, remember, was still not a country. This was one way of putting it on the map.
Eh bien voilà, polonium it is.
Marie next turned her attention to the second mystery element.
She finds the activity is through the roof. It's nearly 1,000 times more active than even her uranium sample had been.
Marie's polonium sample had not been pure enough to yield a unique spectral line. Would this new, more powerful element pass the test?
By 1900, spectroscopy was often seen as the gold standard for identifying the materials you're working with. And if Marie Curie wanted to make some claim that she'd found, in fact, a whole new element, she was going to have to meet the chemists on their own terms. She'd need spectroscopic evidence.
Regardez ici. Il y a une ligne par ici.
Marie's sample showed the presence of the well-known element barium, but it also revealed a pattern of spectral lines never seen before. Strong evidence that she and Pierre had tracked down their mystery element.
She could tell that she had an element that hadn't been seen before because the spectral lines she got were different.
And in the notebook, Pierre writes in very bold ink the name they decided to give the new element, radium.
But in the 19th century, there had been scores of claims of elements that later proved not to be elements at all. You needed to do more.
To satisfy the chemical community, a spectral line wasn't enough. They had to see the real stuff, which could be weighed, which could be measured.
It was important, as you would with any other element, to isolate this element, to weigh it, and to place it on the periodic table.
So in order to be absolutely certain, she had to have pure material, and that's what she set out to do.
It was my mother who had no fear of throwing herself into that daunting task. Without personnel, without money, without supplies.
To isolate even a speck of radium, Marie would need to process huge quantities of pitchblende, a job too big for her tiny laboratory. The only space available for this work was a drafty old shed, once used as a dissecting room for the school's medical students. As Greer Garson and Walter Pidgeon showed in the 1943 film Madame Curie, the Curies worked tirelessly to separate the radium from tons of pitchblende residue they had shipped from a mine in Bohemia.
Sometimes I had to spend the whole day mixing a boiling mass with a heavy iron rod nearly as big as I was. I would be broken with fatigue by the end of the day. And yet we spent the happiest days of our lives in this miserable old shed. An entirely new field was opening before us.
Marie soon realized that radium was a smaller part of the pitchblende than she ever imagined. Less than 1/1,000,000th of 1%. Isolating it was going to be an enormous job.
Marie's daughter said that had it been up to Pierre, he might not have taken the next step.
The world has done without radium up to now. What does it matter if it isn't isolated for another 100 years?
I can't give it up.
There is a special passion which goes with the discovery of elements, and a line in the spectrum is not enough.
She was after an understanding of nature, and there was very, very little that would stand in her way.
In 1902, after 4 years of arduous work, Marie finally succeeded in isolating 1/10 of a gram of radium chloride from 10 tons of pitchblende residue.
4 years to produce the kind of evidence that chemical science demands.
All of this effort so that she could actually convince the remaining chemists that this was a real, honest-to-goodness element.
She measured radium's atomic weight at 225.9, very close to the current value of 226. And she placed it correctly in the periodic table.
Radium officially existed. The incredulous chemists, and there were still a few, could now only bow before the facts, before the superhuman obstinacy of a woman.
Here she was, still basically a graduate student, and the whole world was beginning to talk about her discoveries. In just these 4 years, she's now discovered 2 brand new elements. Even more important, she's shown that this strange emanation, this radioactivity, is a feature of matter, not specific to one quirky little substance. And she's also developed a quite impressive technique for finding more.
This was the beginning of identifying elements by their radioactive power.
The same technique would soon be used by others to identify more new radioactive elements. In 1903, Marie Skłodowska-Curie became the first female scientist ever awarded a doctorate in France. By then it was clear radioactivity was a pivotal scientific discovery, deserving of recognition.
There's no doubt that Marie Curie had done the lion's share of this work. And yet, when the time came to recognize this work, it very nearly went to other people.
A number of prominent French scientists nominated Pierre Curie and Henri Becquerel for the Nobel Prize in 1903. And in this letter, they didn't mention Marie Curie at all.
One of the nominators was Gabriel Lippmann.
It's quite remarkable, since Gabriel Lippmann was her teacher, her mentor. He actually presented her very first paper to the Academy. So he knew about her importance in this work and how central she was to these discoveries. And yet this cabal of Frenchmen just left her off the list. The idea that she could be an important scientist just didn't occur to them. She was totally invisible.
Pierre, and we have to give him total credit for this, turned around and said, I did not conceive of this idea. I helped with the work, but it was someone else's idea that made it possible, and that's Marie Curie.
Pierre was adamant that Marie needed to be included. He immediately wrote back and said, wouldn't it be better, from an artistic point of view, to award the prize to Marie Curie and to me?
In the end, Marie did share in the Nobel with Pierre and Henri Becquerel. She would go on to win a second, all her own. But the real prize was the magical substance for which she would always be known. Some nights, the Curies would stop by the laboratory to admire the element Marie called my child.
They arrived in the Rouleau Monde. Pierre put the key in the lock. The door squeaked and admitted them to their world.
Eve Curie, in her biography of her mother,
Don't light the lamps.
describes the wonder of the Curies as they went into their lab one night and saw these glowing vials.
From all sides, we could see gleamings suspended in darkness, like faint fairy lights.
Do you remember the day you said to me, I would like radium to be a beautiful color? Radium had something better than a beautiful color. It was spontaneously luminous.
The fact that radium glowed in the dark seemed magical, but it was also troubling because it almost seemed to violate some kind of fundamental physical law.
Scientists had known for some time that light is a form of energy. So if you distill something and it suddenly glows in the dark, you have to ask the question, where does that energy come from?
It's not changing shape, it's not interacting with the environment to get this energy, but it's just glowing infinitely. And we had no idea why it did that.
It was Marie who had the flash of insight. Perhaps some types of matter were changing from one kind to another, their atoms splitting apart and releasing energy in the process.
This theory of the source of the energy is very seductive. It explains radioactivity very well.
But it was an idea many chemists refused to accept.
Tell me, please, how much radium salt is there in the entire Earth? A few grams. On this shaky foundation, they want to overturn our understanding of the nature of matter.
Even the Curies were reluctant to accept it.
The Curies themselves, they wanted to think of elements as immutable, unchangeable parts of nature.
The idea that one could have transmutation from one element to another was very disturbing, even to her at first.
But the Curie's discoveries inspired others around the world to pursue this daring theory.
The idea that finally got pieced together was that the energy was in fact coming from the disintegration of these atoms themselves. Radioactivity was a sign that the atom itself was unstable. It could break apart.
This discovery implied something even more profound. Up to then, most scientists had believed atoms were the smallest units of matter, solid, unsplittable lumps. But if radioactivity was atoms falling apart, there must be even smaller pieces inside, still awaiting discovery. Thanks to this Polish expatriate, this graduate student, this young mother, scientists hoping to solve the mystery of matter now had a pressing new question to answer. What's inside the atom?